Welcome to Chapter 6, Thermodynamics. We'll study heat transfer and energy transfer in molecules. Some learning objectives are there for you. We get into some phase changes a lot and talk about the heat transfers that are going on there. Is the freezing of water exothermic or endothermic? So water is going from a liquid to a solid. The particles are moving less, and if they're moving slower, they have less energy than they did before. So if the energy is going down, they must be losing the energy. This is an exothermic process. Since they're moving slower, they're losing energy to get to the solid state. Here's a couple more examples. And this time we have to understand system and surroundings. So because one thing gains energy, the other loses energy in an equal amount there. So in this case, the system is underlined, and are these processes exothermic or endothermic? Your hand gets cold when you touch the ice. Well, your hand is getting cold because it is losing energy. All the energy is going into the ice. So that's part B. The ice gets warmer when you touch it. If it's getting warmer, it must be gaining energy. So the ice is endothermic there. Water boils in a kettle being heated on a stove. And just the fact that it's being heated, that's kind of a clue that energy is going into the water. Endo. It is warming up. Water vapor condenses on a cold pipe. So there's gas to liquid. It's getting colder. It's losing energy to turn into a liquid. Ice cream melting. Well, if the ice cream is heating up in order to melt, energy must be going in to the ice cream. So that's endothermic. So here's a problem that says calculate the work associated with the contraction of a gas from 75 to 30. And since it's getting compressed, work is done on the system. That means work is being added. So that should help us with the sign at the end. Even if we forget the equation, we should know if it's positive or negative just from that. Our work equation is work equals, when it's we're talking about gas pressure doing work, negative P delta V. Negative is because this is our system. So our system is going to be negative P delta V because there's a sign change in there. So negative 6 atmospheres of pressure. It's pushing the piston. And then the work is being pushed. Now, final change in volume always means final minus initial. So this is 30 liters minus 75 liters. So that's going to give me a negative number. Negative 6 times negative 45. That'll give me a positive answer there. Which comes out to be negative 270. Now the units on this, pressure is in atmospheres, volume is in liters. We actually call those liter atmospheres. So that's part 1, negative 270 liter atmospheres. And that should say ATM, not ATOM. Liter atmospheres. But then the other question is, well, that's not in joules. Joules is kind of our standard energy unit because atmospheres is not really an SI unit. It's a different system. So we need to convert that. So we say negative, our 270, I'm sorry, that's positive 270 because you've got 2 negatives in there. 270 liter atmospheres. And then they give us a conversion. You don't need to memorize this. But we say every 1 liter atmosphere is 101.3 joules. So we get 27,351 joules rounded at the end. 2 sig figs, and since this registers in the kilojoule scale clearly, we will say 27 kilojoules. We always report the numbers where they register. Calculate the change in energy of the system if 38.9 joules of work is done by the system with a heat loss of 16.2. This one you just need to keep track of the sign changes, and the words there are the sign changes. Remember, there's no such thing as negative energy. It's just energy in or energy out. So done by the system means the system is doing work, it is losing energy, that's a negative value. And a heat loss also gives that negative 16.2 a negative value. So my energy equation, the energy of the system is going to be heat plus work. Work is W, heat is Q. And since the work of the system it's negative 38.9 joules, and then the heat of the system, I'll still put a plus sign there, it's negative 16.2 joules. Okay, we add those up and we get negative 55.1. And this is a really simple multiple choice question because you have to make those numbers positive or negative. When you add them up, there's 4 choices. Just make sure you understand if heat is going in, work is going in or out, with those words as well as with the numbers. So the last question here with 6.1. A piston is compressed from a volume of 8.3 to 2.8 against a pressure of 1.9. So that is my work information up here. That tells me how much work, negative P delta V. In the process, there is a heat gain. There's my heat down there of 350. Calculate the energy change of the system. So our energy change is heat plus work. Okay, so the heat is 350 joules, positive. That's pretty straightforward. The work, however, we have to calculate. So we just kind of put everything together here. 1.9 atmospheres. And final minus initial, we've got 2.8 liters minus 8.3. It's being compressed. That means energy is being added to the system. Work energy is being added. So that's going to give me an answer of 10.45 liter atmospheres. Now if you stop there, that is not the amount of work energy that we want. Since that's in liter atmospheres and the heat is in joules, I can't just add those until they're in the same units. Okay, it wouldn't make any sense to add them if they're in the same until they're in the same units. So our extra step here with the work is, yes, we measure gas pressures in atmospheres, but it's not an SI unit. We need to convert it. 1 liter atmosphere, strange unit there, is 101.3 joules. And that's going to give me, my work energy is 1058.6 joules. Okay, now we can put all these together. So my energy equals heat plus work. My heat is 350 joules. My work is 1058. We'll say 59 with sig figs, because we're going to round it off anyway. And then we get 1,409 joules. And depending on your sig figs there, it looks like that 350 has 2 sig figs back in the problem, which is really to the tens place, because now we're doing some addition. So we're probably going to round that off to 1,410 joules. Technically, this does register in the kilojoules scale. So if you wanted to call it 1.41 kilojoules, you could also report it that way. Either of those is fine, but since 1,000 joules is not really a lot of joules, so we're only talking about a kilojoule. That's kind of right on the threshold. You could report that in joules or kilojoules either way, because it's pretty close to that threshold. So unless they ask, you have a little bit of freedom there. And now we'll wrap up section 6.1.